Micrograd. So this is just a tiny sample Autograd engine, which is under a GitHub repo by Andrej Karpathy. Uh, and like this is pretty cool because it is a Autograd engine for educational purposes. And what is cool is like we can just use this is very small, like it has two files, each with around 100 lines of code at max. And with just this much code, we can implement a full neural network and train it to solve like a linear regression or binary classification problem, simple, which is pretty cool. And we could also implement an API like PyTorch or TensorFlow in that. Yeah, so we'll be discussing this. And another cool thing about this is what Autograd allows us to do is in neural networks, we also need to, while we are back propagating losses, we need to calculate the gradient. And like for the operations that you define in TensorFlow or PyTorch, you never explicitly mention, for example, if you define a function in TensorFlow, which is composed out of various TensorFlow operations. Let's say you stack up a bunch of operations together and make a function, but you never, uh, okay, and you have a function and you use that function in a neural network forward propagation, but you never implement a backward propagation on your own. So the reason you don't have to implement a backward propagation on your own is because TensorFlow or PyTorch, they have a automatic differentiation functionality, and Autograd engine, our tiny Autograd engine, would allow us to do something very similar. So how TensorFlow's or PyTorch's automatic differentiation works is, let's say we have a function in TensorFlow made out of various TensorFlow operations. Each of the TensorFlow operations would have a, you can imagine that each TensorFlow operation is like a building block, and internally TensorFlow has a backward implementation for each of the fundamental operation. And when the function itself is made out of multiple such operations, since we know the backward propagation for each fundamental operation, we also, TensorFlow is smart enough to figure out that what the formula for the backward propagation of the entire function would be. Okay. So I think it is pretty easy to follow the code. The main file is this engine.py, and you can see that just 100 lines of code. And I'll just, like, you can watch the video, but the summary, if you just look at the code and watch this video, I think you should be able to follow. Like it'll cover the video. You don't have to watch the video itself. So let me just explain the code in brief. So what Andre says in the video is that let's say we have a computational graph, and by computational graph I mean, let's say we have a computation which does something like d is equal to a times b plus c, and TensorFlow, PyTorch, all of these deep learning libraries, they represent these computations as a computational graph. So maybe they'll implement a node which represents the multiplication operation, which gets two values as input and produces one output, and then like this operation plus operation takes again two inputs and produces one output. So for each value, we'll, in the code he defines a class value, and which corresponds to, like, let's say the value d here or value a here, b here, c here, all of these are values. So let's say we are considering value d. So for each value, like the value d, we would have the following parameters. So the first parameter is op. Op, like op means which operation this value was created from. So a, b, c, these values, for these values op value will be null because they weren't created, they just got initialized. And for D, the operation would be plus. Okay, and previous for every value is like the set of values from which this current value was produced by uh, operating by a operation, like the plus operation, for example. The grad is grad represents the gradient of loss with respect to current variable. So let's say d is equal to a b plus c and loss is equal to some function of d. So grad for d would be the gradient of loss with respect to d, and backward for the function backward for each operation, like we say for each value, would define a function defining how the gradients flow to uh, the children to the previous values. So we use this function to update the gradients of the two previous values of this current operation. And then finally, he also defines a backward function, this backward function. And when we apply this backward function to a value, let's say for example we apply backward function to t, so it will back propagate the gradient values from d to all of the predecessors of d. So predecessors of d, or even better example would be loss is a function, like this function is a unary operator. So for loss, the backward calling backward function on loss would update the gradient values for d, c, a, b, all of these, and all of these are predecessors of f. So the way it works is we first do a topological sort on the current node, and then iterate on the list that we get from the topological sort. We iterate on the reverse list, and for each node as we iterate, we do a backward. We call the backward function to update the gradient values for the previous values. Okay, and so a couple of things to observe in the code is that in the backward function we do a plus equal to rather than a equal to, because of operations like b is equal to a plus a. So for example, for these sort of operations, if we just do self grad is equal to out grad, instead of del b by del a being 2, it will just be 1, which is not correct. And also for this statement we write this statement so that we are able to support operations of the type a b. Value data type is equal to value data type plus integer data type. And in the video, Andrej implements tan h at two levels of complexity. One is he directly defines tan h as a function and also implements a backward function for this operator, for this value. No, defines tan h as, wait, do we have implementation? No. Okay, anyways, he defines tan h as a function of the value and also a backward function. And on another level of complexity, he composes tan h from various fundamental operations like exponentiation, power, division, multiplication, division, subtraction. So this is somewhat similar to like a parallel you can draw is these are fundamental TensorFlow operations, and this is like your own let's say your own function, which is maybe not made out of TensorFlow operations directly. Maybe like a function that you implement in CUDA. Yeah. So let's say you're using TensorFlow and you want to implement your own functionality that you cannot compose out of TensorFlow operations. Uh, let's say in the first case, actually, you can implement this out of TensorFlow operations. So you get the second case in this example where you compose your function out of fundamental TensorFlow operations. And since you are composing your function out of fundamental TensorFlow operations, you using TensorFlow automatic differentiation, you also know the gradients. So everything is automated for you. But on the other hand, if you cannot implement your functionality out of fundamental TensorFlow operations, or let's say for speed reasons, you have to implement your function in CUDA as a kernel, then TensorFlow has no way to know how to calculate gradient for that function. So you'll have to like define this as a CUDA kernel, and for the forward propagation and for the backward propagation, you would also have to write a CUDA kernel or just a normal C or Python implementation, which for the backward propagation, because TensorFlow doesn't know how to calculate gradient for the backward propagation for this function written not in TensorFlow but in CUDA directly. Yeah. So yeah, this is the idea. And okay, and in this file neural network.py, he just uh, implements something similar to PyTorch API, where he defines a neuron as um, as defines a neuron as uh, a set of values. So neurons are represent a set of uh, like a set of values W and a B value. So all of these are parameters for neuron. Then moving on to the next level of abstraction, from the neuron we get a layer which is composed out of multiple neurons, and from layer we get a full full MLP, which is made out of layers. Yeah, and a simple neural network training loop would look like we have inputs and we have outputs. Uh, like for each training sample, training data sample, we have the input value and we have an output value, and our goal is to minimize the loss function. So when we feed the outputs to the loss function, we get a loss value. So according to our implementation, we do a forward propagation um through the neural network to get the loss value, and then we just call loss.backward to calculate the gradient values of all the parameters in the MLP. Then for each parameter, we do value plus equal to minus step size into gradient for that parameter value, and this actually updates the parameter values such that the loss is um, like reduced a bit from the previous iteration. Then after this step, we reset all the gradient values to 0 for the next round of backpropagation. So this is just one um, like this is just one iteration of the entire batch size. So in gradient descent, we do these three steps, that is forward pass, backward pass, and update parameters, and we do these steps for like multiple number of times, and each time is called an epoch. So we do this for multiple epochs. Yeah, and the results are Andrej Karpathy is able to train um a neural network on a binary classification problem he shows, which is pretty cool with just 100 lines of code or 150 lines of code. Yeah, so I think the main takeaway from this project is how complex libraries like PyTorch or TensorFlow, like when you um, try to dig into their source code, it's it's very confusing to find an implementation of, let's say, any function, a simple function like relu or tan. Only for trying to find that implementation would take you a long time, because you need to look for that function and then follow another link. It's pretty confusing. So what I'm trying to say is that a library like TensorFlow, which is so complex, can ultimately be broken down into, functionality wise, can be broken down into something as simple as Micrograd. Like, obviously, Micrograd is written just for values, which are scalar values, whereas TensorFlow, PyTorch, they operate on tensors, and then there's a lot of optimizations that happens on in these libraries compared to our simple Micrograd. But the at the fundamental level, both of these are the same thing. So it this project really gives an appreciation of, lets us appreciate the simplicity of the problem, like in its basic sense, but also how TensorFlow, PyTorch, like they evolved through the time, which is pretty neat.